Okay, so I think we can start. Let me just begin by reminding you where we stopped yesterday, and then I'll do an example of that because I didn't have like a chance to do an example yesterday. So the very last thing that I mentioned yesterday is like um, if you have a function, so let's say that you're given a function, that's your input, okay? I'll make it continuous just to not make our life too hard. So let's say you're given a continuous function. Um, okay, and the goal would be to find a polynomial that is of a given degree. Again, it's kind of like, as you can see, most of the things in this course, you kind of have to fix the degree first. So you choose your favorite degree, and then like you try to find the polynomial. So so you choose as part of the input, let's say an integer, which would represent the degree of the polynomial. It's going to be the degree, and the goal. Okay, so that's kind of where you're given. The goal is going to be to find a polynomial of that degree. So the goal is to find a polynomial of degree n. I mean, I will use kind of like a weird note. I mean, like the notation that I will use for it is kind of like coming from like linear algebra. So I'll just call it a projection, which I'll call it. So this is going to be the name of the polynomial, which in a sense is closest, which will be the closest of all the polynomials of that degree. That's going to be the closest polynomial to the function, which is the closest polynomial of this degree to the function. So it's kind of like similar if you think about it, like as a comparison, it is similar to least squares when we were doing least squares, like I guess last week. The thing is like in least squares, we had like maybe 10, 20 points, data points, and you were trying to find like the polynomial that was closest to those points, right? By minimizing the square. This is kind of like a continuous version of that because now it's kind of like instead of like making the polynomial close to a finite number of points, you're trying to make the polynomial kind of close to another function. Okay, so it's kind of like I'll put that as a remark. It's kind of like a sort of like continuous version of least squares when there are like infinitely many points. Okay, this is like a continuous version of the least squares polynomial regression thing that we discussed from last week. Okay, and kind of like the reason why I'm calling this polynomial projection is because the picture to have in mind, um, and this is kind of like a useful picture, um, is the following. So you can think of you think of the function as some sort of like vector. Um, so this is the function. thought of as a vector in some weird way, And then there's kind of like a plane, and that on that plane, the polynomials of that degree live. Okay, so let me draw the plane. So this is kind of like a plane in quotes. I put it in quotes because it's not really like a plane. It's like what you would call like a vector subspace or a vector space. So this is kind of like the plane where degree and polynomials live. Well, or polynomials of degree at most n live. And kind of like the picture that I'm making is kind of like the way I'm trying to draw the picture is so that the arrow representing the function is not on the plane, which is kind of like a way of saying that the function is not a polynomial. So like the example I'll do in a second is kind of like with e to the x, right? So e to the x is not a polynomial. So that's why it wouldn't live on this plane. But the idea is kind of like on this plane, there's kind of like a point, a vector or a point that is kind of like closest to that function. And so that this is where like this is like the vector representing the projection. So that is the degree n polynomial among all the degree n polynomials that would be closest to the function. Uh, the reason why I'm drawing it this way geometrically is that it is like a projection in the sense that if you think of like having like a light bulb, this is kind of like the shadow. This is kind of like the shadow that the function makes on the plane. And so meaning that this vector, would be perpendicular to the plane. So it really like the picture is like a good guide because it more or less is that is what is happening. It's just that again, if you think of a function as a vector, it's kind of like it has infinitely many entries. So it's kind of like an infinite in infinite dimensions. This is what's going on. So that's kind of like the idea. That is what we're trying to find. So the idea is that this is the closest polynomial in the sense that it's the distance from this point to this point is the smallest. So if you had chosen another point here, the distance would be larger, you see? So that's kind of like the idea of like the method. Um, and there's like a very simple formula for this, which is what I'm about to write. Um, is that okay so far so good? Like at least what the picture is saying? So the key idea is that this polynomial is very easy to find after you have the Legendre polynomials because those are orthogonal. Okay, so the idea is that it's easy to find with the help of the Legendre polynomials. P0 of x, P1 of x, P2 of x, up to Pn of x. The reason why they are convenient is that because since they are orthogonal, them being orthogonal is kind of like saying that they're kind of like a version of I, J, and K. So they are kind of like polynomials which are like at 90 degrees to one another. So they kind of like serve like as axes, as Cartesian axis, all on the space of polynomials of that degree. So they kind of like, there's kind of like P0 is here in some sense, P1 is kind of like here. And then like I cannot really draw this accurately, but PN would be here. So they are all kind of like a 90-degree angles with one another. So that kind of like allows you to kind of like write the projection in a very simple way. And so the idea is that the projection, like this projection polynomial, is going to be a linear combination of these Legendre polynomials. And this is like the main formula. So the main formula is that the projection polynomial, and I'm about to do an example just so that you see it. It's going to be a sum of these Legendre polynomials. So this is going to be a function of x, sorry. Okay. And the idea is like what you need to really specify are the coefficients. So the coefficients can be found using the dot product or the inner product. Okay, where Ci is Fpi divided by the norm of the magnitude or the norm of pi squared. Okay, so this is the key formula. You don't need to memorize this one. I would give it, but like it's kind of like useful to like know where it comes from. So that's telling you how to find the coefficient when you write down the polynomial as a linear combination of the Legendre ones. And I'm about to do an example about this so that you see how it works. Okay, but and again, this is like a very cool formula, and that is at the basis of like many other ideas, like in like engineering and mathematics and physics, kind of like Fourier series is kind of like the same idea, but in that case, it is for a periodic function, and and because it's a periodic function, the bases, that's how you call them, are sines and cosines of different frequencies, and then there's like a dot product, like an inner product between those functions, and they happen to be orthogonal with respect to that dot product, and then every periodic function gets expanded, decomposed in terms of like of sines and cosines. So that's kind of like the same idea of Fourier series. Is more or less what we're doing right here, but with polynomials. And so there are many variations of the same concept that is applied throughout, like different areas of like applied mathematics. So it's kind of like one of the more powerful ideas that you can kind of like treat functions in many ways, in the same way that you treat vectors, and that one, so you can export many ideas that you did in linear algebra to the case of functions. And that's we're kind of like doing like a baby version of that because there are a lot more other things that you can try to do. Um, so let me give you like an example just to make it more concrete so that you see how this would look like. Okay, let's say that the function is just like the exponential, as I was saying. Okay, and what I would like to find is the projection of degree 2. So let's try to find. So again, what is this going to be? This is going to be a degree 2 polynomial. Oh, sorry, like it's in terms of like the Legendre polynomial. So it's going to be C0 P0 plus C1 P1 plus C2 P2. Okay, so it's going to be a degree 2 polynomial that is closest to e to the x. Among all degree 2 polynomials, we're going to find the one that's closest to it. So this is going to be once we finish writing it down, you'll see like it will be like a degree 2 polynomial. So this will be among all degree 2 polynomials, this will be the closest one. This one will be the closest to e to the x. Okay. And so let me just remind you what are P0, P1, and P2. Those are like the Legendre standard Legendre polynomials, which I also would give you. Like you don't have to memorize them, but like we have talked about them before. So P0 of x is just the constant equal to one. P1 of x is x, and P2 of x, if I'm not mistaken, was 3x squared minus 1 divided by 2. Okay, so you see, like one is degree zero, one is degree one, the other is degree two. And then again, like the point of them is that they're all mutually perpendicular to one another. So they're kind of like I, J, and K. Um, because of what we were saying yesterday, the convention, the normalization convention is that if you take x to be one, then you get ones, one, and this makes sense because here you get 3 minus 1 over 2, which would be 2 over 2, which is 1. Okay. So that is enough to kind of like pin it down, like these polynomials. Okay. And so then you have to find Z0, C1, and C2. Okay, so what is each of those things? So now we need the coefficients. So now we need, and you just apply the formula that I was writing a bit earlier. So C0, for example, would be the inner product between F and P0 divided by the length, the norm of P0 squared. Okay, so let's just work out what that means. Okay, so again, the numerator is you know, an inner product is just like multiplying and integrating, right? So it's just like the integral from -1 to 1 of e to the x times 1 dx. Okay, and then what is the norm squared? It's the same. Remember, like I can write the formula here actually, if you want it, so that it's a little bit more explicit. You just do the norm. What's kind of like Pythagoras theorem? So it's like the square root of the integral of the function squared, because the norm is being squared in the denominator. You don't need the square roots, so it just becomes the integral from -1 to 1 of 1 squared dx. Okay. Is that making sense? Like what I plugged in into the formula? By the way, I'm not sure. Like, can scientific calculators find the values for integrals, or can they not? Or can they? Anyone knows? Okay, perfect. Like in practice, like if I ask you to find something like this, it would be super easy to integrate, but like I'm totally fine also if you just plug it into the scientific calculator to find the value for the definite integral. That this is not an issue, because like the point is more to understand the formula. So I just wanted to double check that. But I will try to make sure if I give you something to find on the exam that is something that even if you didn't have like, on the calculator, that you would be able to integrate it easily, so that it's not like an issue. But it's good to know, like, um, so I like the integration, like I don't want it to take too much time, it should be kind of like fast, so I won't give you anything too crazy. um so even e to the x, as you'll see, it's not something that I would give you, because like it would require integration by parts if you were doing it from scratch. So I don't want, like, it would be something more simple, but still it's kind of like e to the x is a nice example. So if you kind of like work it out, like, like at least this one is not too bad to integrate. It's just e minus 1 over e, and then in the denominator you just get 2. And I'll approximate this like in a moment. So these will be like, I mean, this is roughly going to be like 2.3504 divided by 2. Okay, so this is the first coefficient, C0. So C0 is roughly 2.35 of 4 divided by 2. which is, I mean, which is 1.1752. Okay, so that is the first coefficient. Oops, sorry about that. Okay. Is there any questions about how I found this one? Does that make sense? And then you do exactly the same for the other two. So what is the next coefficient? C1 would be the dot product between the function and the first Legendre polynomial divided by the norm squared of the first Legendre polynomial. So again, what does that amount to? That becomes the integral from -1 to 1 of e to the x. Now the first Legendre polynomial is x times the x. And then you do the integral from -1 to 1 of you square the Legendre polynomial, and so you just get x squared dx. Okay. And again, like that's what I meant. Like, if you actually wanted to do this from scratch without any help, you would need to kind of like do integration by parts. Like, so, like it's not something like, I necessarily want you to do. Like, so you could put it either in the calculator or just, again, I'll give you something that would be kind of like a little bit more straightforward. But let me just check my numbers. Okay. Um if you do it anyways, like the numerator should give you 2 divided by e. Well, let's just write it as 2e to the -1 so that it looks a bit nicer. And the denominator for is 2/3. Okay. Um, that is a norm squared. And that, again, you can kind of like simplify it. If you simplify all of this, okay, if you kind of work it out, you should find 1.98. So this should roughly simplify to 1.098. Yeah. Okay, so that would be the second coefficient, like an approximation. Okay. And the last coefficient would be exactly the same formula. Okay, so it would be C2 equals F with P2 divided by the norm of P2 squared. What is that? Again, this is the integral from -1 to 1 of e to the x with P2. P2, I wrote it earlier. It was 3x squared minus 1 over 2 dx. Um, and then you divide by the normal square of P2. So it's an integral from -1 to 1 of 3x squared minus 1 over 2 squared dx. And again, if like I literally used Wolfram Alpha yesterday when I was doing this ones. But let's see. So if you kind of like work it all out, they should like the exact answer would be e minus 7e to the -1. I mean, this one is definitely more tedious if you had tried to do it from scratch, because like you would have required to do integration by parts twice, and it's kind of like annoying. But and then the denominator gives you 2/5. Or well, 0.4, let's say. And if you kind of like, again, simplified all of this, you get 0.3578. So that means that C2 is roughly 0.3578. Is that okay? Is that making sense, the three coefficients? Okay, so those are the coefficients of uh, that give you the linear combination of the polynomial of degree 2 in terms of the Legendre polynomial. So what is the projection? The projection, again, so the projection would be C0, P0 plus C1, P1 plus C2, P2. Okay. And again, like the important thing to remember in this decomposition is that these coefficients multiply the corresponding Legendre polynomial because again, the Legendre polynomials are kind of like the correct analog of I, J, and K, or like the standard basis in linear algebra. So it's not like 1x, x squared, x cubed. That is actually ironically not the correct like basis because those are not orthogonal with one another. So kind of like they're kind of like tilted, like if you could like visualize that. So and this will give you kind of like if you write all of this down, like I mean it's not exact, it's like but it's like an approximation, because I did simplify the coefficients. Uh, you would get once, like the numbers that we just found times one because that's the first Legendre polynomial plus 1.098 times x because that was a single Legendre polynomial plus 0.3578 times P2. P2 was 3x squared minus 1 over 2. So as you see, this is a degree 2 polynomial, right? And the coefficients just tells you how much in each of the perpendicular directions it has. Um, and the idea is that of all the polynomials in the world of degree 2, this is the one that's closest to e to the x, at least on the interval -1 to 1, right? Because we, like, as I said, like the convention for us would be on that interval from -1 to 1. And I'm about to show you like how it looks like on GeoGebra, just in case you wanted to see it. Um, is that making sense? Any questions up to this point? So let me see if I can show you that on GeoGebra. Let me stop sharing for a second. Okay, so this is e to the x, right? Like this is the graph of e to the x in orange. I'm trying to show it just roughly between -1 and 1, because again, that is where we're trying to do the approximation, because like the interval of integration was between -1 and 1. So roughly, that is roughly the interval. Let's see if I can. Okay, yes, now it looks better. So what I was saying is that, let me see actually if I can show you the entire formula. Uh, okay. Okay, well, kind of there is between -1 and 1. Okay, so that is a function. And again, these are like the three Legendre polynomials. The first one is just constant equal to 1. The next one is x. And the other one is 3x squared minus 1 divided by 2. So those are the three Legendre polynomials. And kind of we are going to recombine them into a degree 2 polynomial that approximates e to the x, the closest. Okay? So the idea, you can kind of like start like term by term. So that let's call that like, okay, like I don't know if you can if you can see where I'm writing here on input, like at the bottom, like I'm writing k of x, or like actually like yeah, let's just write p of x because I haven't used that one. So that would be the polynomial that I'm trying to approximate it. So if you look at your notes, the first coefficient was 1.1752, right? 1.1752 times the first Legendre polynomial, which was p0 of x. Okay. So, like, you just get like a constant, which makes sense because like that, like, the first, like if you just keep the first coefficient, like that would just give you like a constant term. But then you kind of keep adding more and more of, you add the next contribution to kind of make it a little bit better. So kind of like I'm going to change the formula for P of X. So let's see. So I'm going to, let me delete it again. So P of X is now going to be 1.1752 times P0 of X plus 1.098 times P1 of X. Okay. And that one, the one that you see in green, that is the line of all the lines in the world between -1 and 1. That is the line that's closest to e to the x. Okay. Let me see here. In the sense that we defined earlier, where what does it mean that they're close? It means that if you were to subtract the functions and integrate the difference squared, that has like that would be give you the smallest number. This line. That's basically what it means. Um, and then the next one would be that the actual degree two polynomial that we found would be like all the three terms included. So it would be 1.098 times p0 p1 of x plus 0.3578 times p2 of x. Okay, which is kind of now that's the red one that you see here. So that one does look a little bit better, like actually, like as a degree two polynomial. And GeoGebra, if you look at the formula, oh, actually it doesn't simplify it, which is fine. That's good. It kind of, if you see, let me see if I can. Okay, so there you see like the combination, right? Like 1.1. Yes, yes. So the red one is kind of like the degree to the parabola because a degree to polynomial is a parabola. So of all the parabolas between on the interval from -1 to 1, this parabola is the closest to e to the x with the formula that that we define for distance, which is like again the integral of the square of the difference of the functions. Okay. So that's actually pretty cool. And you can think of it as, again, like kind of like a continuous version of least squares method. So it's kind of like, and as I was saying, like tomorrow and Thursday, we kind of like, we'll start using this idea for more of our purposes of like, approximating derivatives, approximating integrals, a bunch of other things. Um, so like we'll see the applications of this very soon. But even regardless of that, it is like a very useful idea like on its own right because it's kind of like an extension of like least squares to the case of functions, which is kind of like, which again is pretty cool. Um, is that making sense? Are there any questions about this so far, so good? Okay, so I already have spent some time telling you about Legendre polynomials. There's still another type of polynomial that I haven't told you about, which are also super useful in numerical analysis, which are called the Chebyshev polynomials. So that's what I was going to do for the rest of today's class, just explaining to you where they come from, which is they're also very interesting. So like because it's like that's a little bit separate from like this topic. Let's do the 5-minute break now. And then when we return, I'll explain to you what the Chebyshev polynomials are all about. So let me just say 110. And if you want to ask me anything in between the break, you can also do so. I'll pause the recording for a second. Okay, so now we can continue. And as I was saying, like the next topic, that there's another type of there's another important family of polynomials called the Chebyshev polynomials, which are the ones that I'm about to tell you. and they're really, really useful in numerical analysis. It's kind of like good to have some acquaintance with them now. Um, so I will, you know, I don't want to kind of like just write down the formula because then it will look a little bit weird. Where did they come from? So I'll kind of like do like a mini detour explaining where they come from so that you have that idea. Um, but after that, like after I motivated it, it's just like the formulas that, whatever the formulas say. But I do want you to have like some idea of where they come from because it's kind of like actually like a very cool, um, way of like creating them. So that's kind of like interesting to know. The only thing is that it will require just mentioning very briefly certain things about complex numbers. So I'll kind of like, I mean, I know you have seen complex numbers from time to time, and it's not that much that I'll use, but I'll remind you what I have to use about complex numbers. But it's kind of like that is a way to make the connection the more elegant way. So, okay. So, in order to motivate them, as I was saying, I have to say a little bit about complex numbers. So if you remember, hopefully, like what was a complex number? Like, so just like a background, on complex numbers. So what was a complex number? Like you can think of it as if you have a complex number. Well, there's like a very useful way to think about them as points on the two-dimensional plane, like on the XY plane. So usually in the notation of complex numbers, if you have a point x comma y, you write it as x plus I times y, which you tend to refer to that as a number z. So z is like the complex number. Okay. And here I is like the famous square root of -1, right? Where I squared equals -1. Right. So that is like the basic of the complex numbers, right? And in terms of like Cartesian coordinates, and then there was like another way to think about them, like kind of like using more like polar coordinates. So this is kind of like in terms of Cartesian, and the way to think about them using polar coordinates. Also, if you remember in polar coordinates, this is r, right? This was theta, right? And then in polar, like you can write this complex number z as r to the e times theta because of Euler's formula. So Euler's formula said that Euler's formula said that e to the I theta was cosine of theta plus I sine of theta. I think probably you use some of these like in differential equations, I'm sure, like because in complex numbers are very useful for differential equations. So hopefully this looks familiar. Um, but my point is that the reason why I'm mentioning this is that the way you can think about a complex number is in two different ways. You can think about it in terms of x and y. So a complex number, you can think about it in terms of x and y, like as x plus iy, or so this is kind of like the Cartesian version. And you can also think about it in the polar version, which is r times e to the I theta. So both are fine and both are convenient for different things. So there are times where like the polar version is more convenient, and there are times where the Cartesian version is more convenient. Is that okay? Is that making sense so far so good? Hopefully it looks like a refresher. So the idea is that in the same way in which you have regular polynomials, like which are like ones that we have been working with, right? So let's call them real polynomials. Like, what is like a regular, like, and by that I just mean like the polynomials that we have been studying. So like it could be x or x squared plus 1, or like x cubed minus x plus 2, right? Or 3x cubed. Like a regular polynomial is a real polynomial is anything that is kind of like powers of x, right? So, that is kind of like the regular polynomials. You can also talk about complex polynomials. So you can also have complex polynomials where z is playing the role of x. So like, let me just write like a complex polynomial would be something like z or z squared plus 1 or 3c cubed minus z plus 2. Or in general, it would be just like a combination of the different powers of c to the n. Okay. So like all that I'm saying is that once you have complex numbers, there are complex polynomials. That's kind of like the idea, and they kind of like are defined in the same way as regular polynomials. It's just that instead of like using the variable x, you use the variables z. Okay. Okay, and then okay, but you can still kind of like think of these polynomials which are complex in terms of x and y. Okay, so here's like an example. What is z squared, right? Well, z, as I was telling you, is x plus I times y squared, right? And then what is x plus I y squared? That it is, you can use the same formula as a plus b squared. So that's a squared plus b squared plus 2ab. Okay. So this is x squared plus b squared plus 2 times a times b. Okay. And what is this? This is x squared plus I squared y squared plus 2ixy, right? All of this is equal to z squared. But then x squared, sorry, I squared is -1, so right, that gives you x squared minus y squared plus 2ixy. Is that making sense so far so good? Like how I found c squared? Sorry, give me a second. Is that okay so far so good? And here's another one. Like, let me just do one more so that you see like that every time you have like something in terms of x and in terms of z, you can rewrite it in terms of x and y. What would be, for example, z cubed? Z cubed would be x plus iy cubed. Okay. But one way to think about it is that this is like, x plus iy squared times x plus iy, just to use the fact that we already simplified it a bit earlier, like the previous one, right? Because we already had like a formula for z squared. So this would give you, it gives you x squared minus y squared plus 2ixy, right? Times x plus iy. And then how do you do this? You kind of like distribute, right? So you would get, uh, let's do this. Like you get x cubed plus x squared iy. Just to, if anyone wants to follow, like this is what's going on right now. Oops. Okay. And then, then minus y squared x minus iy cubed. So those are the next two. Oh, like actually, let me just use the same color because otherwise it will be, yeah, like otherwise too messy. Like, so I'll just say that this is, right. So when I multiply these x squared with these two terms, this is what I'm finding. When I'm multiplying minus y squared with these two terms, this is what I'm finding. And then the last one, there's only one more to do. Let me see if I can fit it here. And then the last one is okay, 2ix squared y plus 2i squared uh x squared, no, sorry, like xy squared. Is that making sense how I found all the terms? Okay, and then let's just like regroup things so that like the stuff with I is kind of like on one side and the stuff without I is on the other side. But let me just go carefully. So this one had no I, so I keep it. This one had no I, so I keep it. This one has an I, so I will wait. This one has an I, so I will wait. And this one doesn't have an I. It looks like it has an I, but you have to remember that I square equals -1. So I also have like 2I. Sorry, like it becomes a -1, so it becomes -2xy squared. Okay, and everything else that I didn't include will have an I, so let me just factor that I to make it more explicit. So this one had an I, so you get x squared y. This one had an I, so you get -y cubed. And the last one that had an I would be 2x squared y. So there were 6 things, and kind of like half end up with I, and the other half ends up without an I. Like, let me check that this is fine. Like it's x cubed. Oh, right, and then these two can be combined. Like these two are the same, so they can be combined. I mean, they have the same exponents, so you just end up getting x cubed minus 3xy squared plus I. And let's check here whether there's something that can be combined. Yes, there's something that can be combined, right? Because these two can be combined, so that gives you 3x squared y minus y cubed. And now that looks a little bit more clean, right? Is that okay? So far, so good? So it's good. It's okay. I promise the punchline is coming. Like it's actually really cool what's about to happen. But I just wanted to work out some calculations so that you would see what's going on. So just to summarize, if you have going back to what I was saying, you can have z. Z was just x plus I times y. Because of these calculations that we just made, z squared would be what? X squared minus y squared plus 2ixy, right? And c cubed would be x cubed minus 3xy squared plus I 3x minus y cubed, 3x squared y minus y cubed. Okay, so those are the 3 things that we found. And of course, you could continue forever. Like, if you wanted to keep going this way, you would use a binomial theorem, which Newton had found, among other people, I suppose. But I just want to illustrate the point with these 3 because that's kind of like enough for what I need. Uh, so there's something about a complex number. When you have a complex number, you can find its real part. The real part just means like the number that's not multiplied by I. So for example, here, the real part of z is just the number that doesn't have an I, so it would just be x. The real part of z squared would be the expression without an I. So what doesn't have an I is like x squared minus y squared, right? And here the real part of z cubed is x cubed minus 3xy squared. Okay, so the real part of a complex number is just the part that has no I. After you have done all the simplifications, right? You have to be careful because, like if you see I squared is -1, right? So there's no I actually. So it's not just like a identify. Like you have to think a little bit before you identify the real part. You have to use as much as you can that I squared equals -1, basically. Um, okay. Okay. And what's kind of like interesting about the real parts, if you look at these real parts in terms of x and y, they are polynomials in terms of x and y, right? They are polynomials of x and y. So that's kind of like interesting to notice, right? I mean, also the imaginary parts. Like the imaginary parts are like the things next to I, but like the Chebyshev polynomials like focus on the real parts. So these, in terms of x and y, the real parts, like the real part of c to the n is actually going to be a polynomial. And that is almost what the Chebyshev polynomial is going to be. So the Chebyshev polynomial is going to be these polynomials, okay? The Chebyshev polynomials are these polynomials, but these polynomials right now depend on two variables, right? They depend on x and y. So in the Chebyshev case, the way to make them depend just on one variable, you add as an extra requirement that x, y be on the upper half of the unit circle. So the Chebyshev polynomials, like let me explain it. Okay, so what is going to be the Chebyshev polynomial? So they are the real part of c to the n, with the extra requirement that x and y are on the top half of the unit circle. With the extra requirement that x comma y belongs to the top half of the unit circle. And that actually will explain a little bit why I chose that interval to be from -1 to 1. Like this is like the connection to that of the unit circle. So what I'm saying is that, um, you know, what I'm saying is that you have the unit circle, right? X squared. You have the unit circle and the Chebyshev polynomial. Sorry, like let me just draw half of it. I'll draw kind of like the half that I'm interested in. I'll draw the other part half kind of like as a broken line. So what I'm saying is that our point x comma y is going to be here, okay? So because it's on the unit circle, like that will tell you that x squared plus y squared equals 1. So that will tell you that y squared is 1 minus x squared. So the advantage of doing like by asking for the point to be on the top half of the unit circle, then it actually can be considered like entirely like as a function of x. That's kind of like the idea, because then you can substitute y squared as 1 minus x squared anywhere that you see it here. So for example, let me do it for like these cases. Oh, and for the first one, there's nothing to do because it all depends already on x. This was okay, right? So this would be the Chebyshev polynomial of degree 1, and I'll write them in a moment, like more carefully. Okay. But how about the second one? If you look at the second one, it depended on x and y. And then what I'll do is substitute y squared with 1 minus x squared. So this is now x squared minus 1 minus x squared, right? And now that gives you 2x squared minus 1. So 2x squared minus 1 will be the Chebyshev, the second degree Chebyshev polynomial. So this is going to be, so t2 of x is going to be 2x squared minus 1. Okay. And what about the third one? So for the third one, we kind of like do something similar where there's like the y squared here. So let's replace y squared with 1 minus x squared. Okay. So that gives you x cubed minus 3x plus 3x cubed, right? Is that... So this should be 4x cubed minus 3x. And that, let me check that. That's like, I didn't do anything stupid. I think I have them in one of the problems that I gave you. Yes, in class. Oh yeah, like it's fine. So that would be the, like, these would be the third degree Chebyshev polynomial in terms of x. Okay, so t3 of x would be 4x cubed minus 3x. Okay. So and kind of like for a convention, like, the t0, I mean, like if you kind of like follow z to the 0 is just 1, so t0 would be just 1. So kind of like what we're finding is that t0 of x equals 1, t1 of x equals x, t2 of x equals 2x squared minus 1, and t3 of x equals 4x cubed minus 3x. And in general, Tn of x, what is Tn of x? So Tn of x, what is Tn of x? That is the real part, this would be the real part of c to the n with the extra addition that then you have to use that y squared equals 1 minus x squared. And then you use that y squared equals 1 minus x squared. And so that you get something that only depends on x. Is that making sense so far so good? Uh, like how I found them up to this point? Okay, so like this I still haven't even mentioned like what's kind of like the really interesting part about them. Like I mean, it is kind of like cool the way to define them. Like if you like complex numbers are oh, that's a thing. That's a great question. This is like the miracle of the binomial formula. The thing is that like it will always whenever you do the x plus I, you know whenever you do like x plus I y to the n, right? The thing is that when y, this is like that's like a very good question. How Let me see if I can explain it. you know Y is always being multiplied with I, right? So the only way for it to appear in the real part is that if you kind of like have like even powers of I, because that's the only way to turn those into, that's the only way in which like the I will disappear. So what I'm trying to say is that i- in the real part, it only appears even powers of Y appear. It never going to have like an odd part. Is that making sense? um because if it like if this had like imagine like this like for example, imagine this had like I to the 5 y to the 5, right? So that's I to the 4 times I times y to the 5. So that would be what, like that's I y to the 5. So the only way for the I to go away is for the power to be even, you know So like there's no odd powers of y in the real part. Is that making sense? Well, the thing is that that is like that's what I'm trying to say because if you have if assuming that you could have something like that in the binomial, that is not really what you have because that would also be multiplied by I cubed. That's the thing because I and y come together, so they're kind of like a single thing. You see? So like it's not you cannot just get exactly on the real part. You never find like odd powers. Yes, yes, yes. That's what I'm trying to say. It's actually very cool, like and it does take some time to kind of like go through it. But like, if you think of I, the thing is that you have to think of I and Y as being coming in. They're kind of like almost like on like with the string, they come attached. You cannot like break them, So the only way for the I's to disappear is that if they were raised to an even power, you see, and that would make Y appear in as an even power because they are kind of like coming pairs. You see what I mean? Uh, No, no, but like, so it's really always going to be a polynomial in terms of x. That's kind of like the miraculous part. Like, it is kind of like, where like the complex numbers really have like so many cool things that happen that, make it all work very, very, very nicely. Um, so I'll make that as a remark because like that's actually like a useful thing to notice. Uh, so like I'll just make it as a remark that, you know, um, so that is what guarantees that it actually is like a polynomial because you are right. If you had had something like y cubed, if you had had like y cubed, then you're stuck because then you have to take square roots, right? And it wouldn't give you a polynomial. So that's kind of what makes it like kind of work nicely. Um, but there's something even better that happens, which is what I'm about to explain. Okay. And that's like this is what also makes it like really, really cool thing. Like the thing that about is about to happen. So here it comes. Why am I choosing like the top half of the unit circle? Because of polar coordinates, right? So if you have the top half of the unit circle, if you have x squared plus y squared equals 1, that means in polar that r equals 1, if you remember polar coordinates, right? So when you had a point x comma y, right, in polar x is r cosine of theta, right? And y was r sine of theta. Let me use a color that I haven't used before. So let's say theta is here, right? But because r equals 1, right, then that means that this is just cosine of theta comma sine of theta, right? So on the unit circle, right, on the unit circle, you can say that x is cosine of theta and that y is sine of theta, right? So now what I'm going to do is use that x is cosine of theta to rewrite these polynomials instead in terms of cosine of theta. So I'll rewrite them in terms of the angle. So for example, t0, t0 was just 1. There's nothing to rewrite because that doesn't depend on x, right? But how about t1? T1 was x, but x is cosine of theta. So this becomes cosine of theta, right? What about t2? T2 is 2x squared minus 1. If you use that x is cosine of theta, you get 2 cosine square of theta minus 1. Okay, and of course, like I don't expect anyone to remember these identities, but like cosine and sines are full of trig identities. So there is an identity for 2 cosine square of theta minus 1, which is cosine of 2 theta, actually. Uh, okay, and then let's go with the next one, T3. T3 is 4x cubed minus 3x, would be 4 cosine cube of theta minus 3 cosine of theta. And again, who would remember this? But there, if you kind of go through like the trick of it, like there's again, like using all the trig identities, this is cosine of 3 theta. Okay. And so I don't know if anyone wants to take a guess. Like I didn't write like what Tn is in terms of x, right? But anyone wants to take a guess on what it should be in terms of like theta, just based on the pattern. Just to make it more clear, this is cosine of 0 times theta, right? It's cosine of n theta. So in terms of theta, the formula for the Chebyshev polynomials is super elegant. It's just cosine of n times theta, which is like again, is really really cool. Well, no, in this case, like it is like indexed properly, so that it's just like because like 2 is with 2 here and 3 is with 3 here and n it would go with n. So it is fine. Like you don't need to shift it by 1. Um, n theta does work in this case. But that is also like a great formula. So kind of like the idea is that in terms of theta, the formula for the Chebyshev polynomial is like very straightforward. Okay. And like the thing is like I could have started like what is traditional sometimes is that you just write this formula. You write this formula and you say, okay, that's a degree n Chebyshev polynomial. But if you just write it this way, it's not super clear it's going to be a polynomial when written in terms of x, right? Like it is kind of like miraculous. So it's kind of like nice to see it like kind of like backwards, so that you kind of like start with in terms with x, and then you do this, and then you have like the formula, like you have like this formula, like which is very clean basically, which is really cool. um Now, what makes them like really interesting as well, I still like again, we'll see why they're useful for numerical analysis. I still haven't told you that part. That's what we'll discuss like um later in the week, and probably early next week. But what's interesting is that these polynomials are orthogonal as well in terms of theta. And that's kind of like a very like remarkable fact, because like they were found in completely different ways. So this is like another cool fact, or like which is also very useful. These polynomials are also orthogonal when you do the integration in terms of theta. And so what do I mean by that? Like, so here, what I mean is that, like, like first, like, this is important to notice, like the theta, what is the values that theta take in polar coordinates for the top half of the unit circle? The theta goes from 0 to pi, right? Like, so theta here goes from 0 to pi, okay? So what I'm saying is that if you have two functions in terms of theta, if you have two functions that depend on the angle theta, you can integrate them in exactly the same way that we were doing before for x. So when you have f of theta and g of theta, you can do their inner product would be, in this case, the integral from 0 to pi of f of theta times g of theta d theta, okay? So it's kind of like the same formula for inner product that we had before. More or less, is that like before it was in terms of x, now it will be in terms of theta. And what I'm saying is that if you take this formula for the inner product, then in terms of theta, these polynomials are orthogonal. So like, for example, what do I mean by that? So again, like, let me just take T0, T1, and T2. Oh, let me copy paste them. So I'm about to erase this, but T0 was 1, T1 was cosine of theta, and then T2 was, I mean, either way could be useful to have them written down. Okay, but like, for example, what I'm saying is that if you take these three polynomials in terms of theta, and their inner products with this formula, then you get 0. So for example, let's do the first one, which is the easiest one. Like, what is T0 with T1? That would be the integral from 0 to pi of 1 times cosine of theta d theta, right? So what is the integral from 0 to pi of cosine of theta d theta? That is just um, like sine of theta evaluated at 0 and pi, and sine vanishes at those 2 points, right? So that gives you 0. Okay, so this first inner product um, is 0. Okay, like, so T0 and T1 are orthogonal in terms of like the theta variable. Um, how about T0 and T2? Okay, how about T0 and T2? And that would be the integral from 0 to pi of what is T0. T0 is 1. And what is T2? Like, you can write it as cosine of 2 theta. Actually, that one works better. And you integrate this with respect to theta. And again, that is kind of like, you do like a U sub if you want to kind of work it out. Like, that gives you what? Sine of 2 theta over 2 at 0 and at pi. Okay. And that also, because sine of 2 pi and sine of 0 is 0, like that also gives you 0. Okay. And like, for example, if you did like the inner product from between T1 and T2, That gives you what is T1, that's cosine of theta. And then, I mean, it depends on which I think it's better if you write it like as 2 cosine square of theta minus 1 d theta. Okay. And then, like, to do this integral, like if you wanted to like like you can break it apart. So like that would give you 2 cosine cube of theta minus cosine of theta d theta. But this one we already know integrates, we already know that this one integrates to 0. So you just have to integrate from 0 to pi of 2 cosine of cube of theta d theta. And then you can do like like a hopeful, again, like I just want to show you how you would do it. Like, we will use this as a matter of fact. But how would you integrate this from calc to, like, you would write like cosine squared as 1 minus sine squared, right? So that you can do like a u sub u equals sine of theta, um, and then and then you will find out that this also integrates to 0. But I mean, or there might be an easier, faster way to do it. But all that I'm saying is that you would do like u equals sine of theta, and then the u is cosine of theta d theta. Okay. So all that I'm saying is that, like, you can check kind of like that, like in general, no, as long as n and m are different, like you will, like, you could prove that these, like, inner products are always diff 0. So in fact, so like kind of like for free, this happens for free. Like, it's not something that we were trying to find them this way, but for free, these polynomials happen to be perpendicular to one another in terms of theta. Okay, which is kind of like amazing fact, like a very useful thing as well. And this is kind of like more related to Fourier analysis, which is not like a direction that we would take, but this is kind of like close to how, like, again, when you do Fourier series and Fourier analysis, um, you kind of like do the dot products and things like that because you rewrite everything in terms of theta. So it's kind of like close to that idea. Um, okay, and maybe I'll mention this tomorrow because I feel like I have already given you a lot of information. What's kind of like cool, next time I'll let me just write it that way. Like so tomorrow I'll explain that if you had the integral from 0 to pi, there's a way to, it's kind of like a change of variables. You can see this as an integral in terms of like x. If you do like a change of variables, like I'll explain this next time, which is like x equals cosine of theta, so that the x is minus sine of theta d theta. Well, I guess I'm doing it right now, but what does that give you? That gives you that the x is, um, you know, minus root minus, let's see. Sorry about that. Like if you took out two, which you must have, like, this is one of these trigonometric integrals that you would have done. So that tells you that dx becomes dx over root of minus 1 minus x squared gives you d theta. So like you can rewrite all of this as an integral in terms of x. And so what you would find is like the integral from when you change the bounds from 1 to -1 of f of x, g of x, and then d theta is now minus dx over root of 1 minus x squared. But because it's kind of like ugly to have the minus here, and you flip the bounds, and if you remember, like the way to like the price for flipping the bounds is you get a minus sign. So this kind of can be rewritten. this way. So kind of what ends up happening is that in terms of the x variable, in terms of the variable x, the functions are, the polynomials are orthogonal. They are orthogonal, but not with respect to the regular inner product that we talked about, but with something that's called like a weighted inner product, because the idea is that you kind of like have changed like the scale here. So this is called like, but I'll mention this like next time because it's also like a useful idea. So this is called like a weighted inner product because it has like this extra factor. This it has this extra factor of root of 1 minus x squared. So that means that kind of like the points are not being counted in the same way because there are like some points that are more important than the others. But I'll mention this like tomorrow. But my point is that from this perspective, in terms of x, these polynomials are still orthogonal, but not with respect to the standard inner product that we saw, but kind of like a distorted version of it, which is this weighted inner product. But again, this is like better to mention it next time on Wednesday, so that it's more refreshing. But yeah, I think like um, at least I wanted to kind of like explain where they come from because it's kind of like an interesting idea. So I'll stay around if there are any questions, but if not, like we can stop here. Actually, anyone?